Note page 210. So this is page 210. This is a quick review of heating curves or cooling curves in reference to energy transfer. So let's do some labeling. So since segment AB is at the lowest temperature range, temperature increases as we go up the y-axis. So the phase of a sample at the lowest temperature range would be a solid, and think about those particle diagrams and how we draw them. Segment CD is in the middle of the temperature range, so this probably represents when our sample is a liquid, and we'll draw a very messy particle diagram. And then segment EG is in the highest temperature range, so this would represent our sample in its gaseous form, and particle diagram, no touching allowed. So notice the things that we have in common with segment AB, CD, and EG is that we have a change in the temperature. So each of these segments represents a change in the temperature. And one of the things that I've asked you to memorize and connect with temperature, if the temperature is changing, then the motion of the molecules is changing. So we have a change in the kinetic characteristics of the molecules. So I'm going to put a change in the kinetic energy, KE. Okay? Now, we have two other segments where they show no change in temperature, and they are sandwiched between two different phases. So this represents a place of phase change. And since segment BC is sandwiched between the solid and liquid, that means that any solid sample is changing to its liquid form, and any of that sample that's already liquid is reforming as a solid. So where BC hits the y-axis, we could label that temperature as the melting point or freezing point of the sample. Similarly, segment DE, we see that there is no delta T, and that segment DE is sandwiched between the liquid and the gaseous phases of the sample. So we need to recognize that this is also a phase change. And in this particular segment, it represents any of our sample that's liquid is changing to a gas, and if it's already in the gaseous form, it's condensing back to as a liquid. Now, if we follow segment DE all the way back to the y-axis, and where it strikes a temperature on the y-axis, we can label that as the sample's boiling point or condensing point. Now, we need to be able to make calculations for each of these individual segments. And if you look down lower, you have two basic Q formulas to use. So Q equals MC delta T versus Q equals M times H. So since segment AB, CD, and EG have a delta T, a change in the temperature, it should make sense that if we're calculating Q, we should be using MC delta T. So I'm going to write that carefully here. So Q equals MC delta T. MC delta T, and then once again here. Now, for the other segments where there's no temperature change, we should not be using Q equals MC delta T, because the delta T would be 0, which then if you multiply any other values by 0, your product is 0. And energy is definitely being transferred between B and C and D and E. It's just not recognized as the kinetic form of energy or characteristic, but it is being absorbed and released in the potential form. So when there's no delta T going on, that means we have a change in the potential energy or stored energy. And with this, we should make a correlation of looking at our particle diagrams. So solid, very, very organized, kept in fixed positions. Where liquid, there's less organization, no true fixed positions. So that means that the stickiness or the strength of the attractions between these molecules has changed. So whenever we have a change in the PE, we have a change in those intermolecular forces or attractions between the molecules. Therefore, we need to use our other Q, which is M times H. And so taking a look here, so Q equals M, and now the H. So since this represents a point of changing between the solid and liquid, we would use the M times H, and it's the H of fusion. And you need to remember that fusion is another way of saying the idea of melting. Whereas segment DE, we're changing between liquid and gas, a different set of phases present. So we would use Q equals M times H, but we wouldn't use the heat of melting or the heat of fusion. Instead, we would use Q equals M times H of vaporization, because vaporization is the idea of a liquid changing to a gas. Now, for water, the heat of vaporization, you can find that on table B for water, and same thing for heat of fusion, you will find that also on table B. So as we look at from point A all the way up to point G, okay, we should recognize that there is an increase in the KE and PE as we go from point A to point G. So overall, point A to point G, we see an absorption of energy, so absorb heat energy. So that means that this process, point A to point G, is endothermic overall. And if we look at it from point A to point B, taking a look at how we draw our particle diagrams, we should see that overall there's a decrease in the IMF strength. And because of that, from point A to point G, look at our particle diagrams, they have less and less order. So we see an increase in the entropy. So this is moving from A all the way to G. And if you can understand those ideas from point A to G, then if you looked at this in the reverse, then G back to A would be exothermic, a release of heat. Look at your particle diagrams, they're becoming more and more ordered in fixed positions, so those IMFs or attractions must be strengthening, and everything is becoming more ordered, so less entropy. Okay, looking at two Q calculations, two examples. So reading through this problem, calculate the amount of energy. So if it's the amount of energy, our unknown is Q. So that is our unknown. Okay, we have 155. We see that it's tagged with a G, so that must represent a mass. So we have our mass value. Okay, now we see that we have a temperature 1 and a temperature 2. So we have a delta T. And now we are told that it is water, so we can look up the C, and that's from table B. Okay, so now take a look. We have a delta T present, and there is one phase of matter. So when you're reading through the problem, the information tells us that there's a temperature change and there's one phase of matter. That's our clue that we use Q equals MC delta T. So Q equals, for M, we'll put in 155 grams. For C, we'll look at on table B, and it's 4.18 joules per gram degrees Celsius. And now we'll show our work for delta T. And remember, delta T always equals temperature final minus temperature initial. Or if this was math class, maybe instead of final, it'd be second temperature minus the first temperature. So our temperature ends at 45.0 degrees Celsius minus where it started, 20.0 degrees Celsius. So this right here is a great example of showing your correct numerical setup. Calculated answer. So if you put this into the calculator, you get this number of 16197.5 joules. This is a calculator answer, but you may need to put it into a final sig fig answer. So our measured mass has 3 sig figs in our measured temperatures, okay? And if we calculate that difference, the difference is, so that equals 25.0, which is also 3 sig figs. So that means we need to keep 3 significant figures, so 161. But the 9 to the right of the 1 would make it round up. So our sig figs are 162, but these values don't represent the same value, so we need a couple of placeholders there. So 16,200 is pretty similar to 16,197 joules. So this would be a final SF answer. Okay? Now, looking at the last problem on this page. So once again, it asks us to calculate the amount of energy. So Q, once again, is the unknown. We see 155 tagged with a G, so we should recognize that as a mass. And notice it says at a particular temperature. So that means no delta T. So our information tells us there is no delta T present. And now there's a very important word, melt. And when we see a word like melt, that means that we are changing between the solid and liquid phase. So we have 2 phases present. So when there's no delta T and we have 2 phases present, we need to use the M times H. So Q will equal 155 grams. Now it says melt, so that means H of fusion, the heat of fusion, because fusion's another word for melting, and you find this on your table B, and when you look it up, it is 334 joules per gram. Calculating the answer gives us, if I did this correctly, 51770 joules. So that's a calculator answer. And taking a look, we have 3 sig figs, so if we have to keep 3 significant figures to get to a final answer, we would keep the 517, but the next digit would make the 7 round up. So our sig figs in the final answer would be 518, but 518 does not match 51770, so that means we need a couple placeholders to end with a similar value. So this would be a final sig fig answer.